Hey everyone, so this week's tutorial video covers a very interesting question. So I was just going through the textbook, the differentiation chapter, and I saw this really interesting question. I've actually never seen this question before on the exams, but even the textbook, I can't remember correctly where this question was, but I think this question is really interesting. It's about finding the second derivative of parametric equations. And yeah, it's an interesting question with a unique and very weird way of solving it. So have a look on the video next, and hopefully you should be able to solve this question. And that question is for the parametric curve given by x equals t squared plus 1 and y equals t bracket t minus 3 squared, find part A, the gradient function dy dx, part B, the second derivative or the gradient of the gradient function d squared y dx squared. Now this question is interesting mainly because of part B. Part A, everyone should be able to do it by this point, hopefully. So let's go into part A. We have to use related rates to help us solve this because we don't have any function, we have a pair of parametric equations, and both of them are in terms of t. To solve for dy dx, we use related rates to help us. That's dy dt multiplied by dt dx. The reason we do that is we know y is in terms of t, so if you find dy dt, then you multiply by dt dx, you can get rid of the dt's, and then you have dy dx. So in that case, dy dt, just derive that, use product rule, should end up with t minus 3 squared, so derive t, get 1, plus derive the second function, we get 2, t minus 3 to the power of 1, this derivative of t minus 3 is just 1, does nothing, and we multiply by t. So that's dy dt. Of course, we also need to find dt dx. In this case, you just solve for dx dt, and then you flip that, you get dt dx. Dx dt is just derive t squared plus 1, we get 2t. Therefore, dt dx is 1 on 2t. And we get our answer. Dy dx is equals to, I'll expand this out right here, t squared minus 6t plus 9 plus 2t squared minus 6t over 2t. So basically dy dt, we just use this function right here, multiply by that function. That's what we end up with, and I'll simplify that on the right side. 3t squared minus 12t plus 9 over 2t. So t squared plus 2t squared, that's 3t squared, minus 6, 12, and 9 is just there over t. Okay, I'll drop that out a bit. Now the good part, this is the interesting bits. Part B, d squared y dx squared, finding the derivative of this function right here. Okay, so before we do that, I'll change this dy dx into something that looks a little bit simpler. So since we know that the gradient of this function is dy dx, or in other words, another way of writing that is y dash, you can replace dy dx by y dash. And we have 2t. Okay, so this is just to help simplify things so that I can explain part B. Okay, d squared y dx squared. Now, if you want to derive the gradient function, which in this case we have 3t squared minus t, 12t plus 9 over 2t, you cannot just derive this. You cannot derive this function in terms of t. So we can't just go, okay, yeah, I'm just going to go d dt, derive that, dy dx, and then that's unfortunately, because if you're deriving this function right here, what you're actually doing in terms of t, of course, is what you're actually doing is d dt of dy dx, or another case, d dt of the y dash, which would not give you d squared y dx squared no matter how you multiply this out. So d times dy dx is not going to give you d squared y dx squared because you still got that t. So no, it's not the same. We cannot just derive this gradient function to give us the second derivative. So how do we approach this question? Well, you have to learn one basic first. How the gradient the dy's dx and the d squared y dx squared came about was, let's just have a look at an example. Y equals x squared, right? If I want to find the gradient function of that, what I actually do is d dx of that function. So in this case, d dx of y would actually give me dy dx, because I'm just bringing y on top. And that would just, well, derive x squared to x. So in this case, if I want to find if I want to find the second derivative, what they actually do is d dx of dy dx. So dy dx is my gradient function. In other words, what is actually happening here is d dx, that gradient function dy dx is up here. Dy dx, it's up here. Treat that as y, treat that as one function. So it should go on top. And what we have is d square y over dx, and then the whole thing is over dx, and what you actually have is d square y over dx squared. Now it's supposed to be bracket right here. It's supposed to be bracket dx and then square, but we have this terminology where you don't have to do that, you just write dx squared. Okay, don't think too much about that part, but this is the important rule right here, this part. If you want to find the gradient of the gradient function, you go d dx, just like always, of the gradient function, which is dy dx. You just replace y with dy dx this time. So we do the same thing. If you want to find the gradient of this function right here, so 3t squared minus 12t plus 9 over 2t, you go d dx of dy dx. The problem, however, is this is our function here has t as its variable. Our formula right here has x as its variable, so we're deriving in terms of x. So we can't do that because we know this function has t. You can't derive a function with t in terms of x, it's not possible. So what you actually do is just replace that dx with dt. So I'm going to do it right here. Replace dx with dt, dy dx. In other words, that dy dx really should just be y dash. So if you want to simplify things, just chuck y dash in here, because I know dy dx looks a little bit weird, but that's what is happening. You derive this function in terms of t now. Okay, but how do you get d square y dx squared? That's what we want, right? That's our end goal. We still got this dt over here, which is going to mess things up really badly. So if you want to get rid of that dt, just like what we did above, right here, you multiply that by dt over dx. So really the second function is just to get rid of dt. So if you times it by dt, you get rid of the dt, and at the bottom, what you actually put is dx. The reason being is if you multiply this out, over here, dy over dx is d square y, and then dx is just by itself because d times dy, numerator, d square y over dx, but you divide it by dx as well, because it's that multiplied by 1 over dx, and what you end up with dx squared, and that solves the case. So this is a little bit confusing, but hopefully you understand this part because it's quite interesting. So finding the second derivative of a parametric curve. Right, and then from there on it's pretty smooth. d dt of dy dx, that just means derive that. So if you derive this, you get dy dx over dt. So let's derive that. Right here, which rule do we use? We use the quotient rule. You end up with 4t squared, so you square the bottom, and then on the top, first of all, you derive the top function. We get 6t minus 12. Then we multiply by the bottom denominator function. Then we subtract the top function multiplied by derivative of the denominator. You just end up with 2 bracket 3t squared minus 12t plus 9. And of course, don't forget, that's just dy dx over dt. we have to multiply that by dt dx as well. And we know dt dx is 1 on t, so that's what you have to do, 1 on t. Okay, so I'm just going to expand this because that looks pretty nasty. 6t times 2t, 6t minus 12 times 2t gives us 12t squared minus 24t, and expand that as well. Minus 6t squared plus 24t minus 18, and the denominator is just 2t times 4t squared, that's 8t cubed. And what we have here is negative 24t, cancels out with that. We can also simplify that 12, 6, and 18 by 8 divided by 2, that's our factor. 6t squared, divide that by 2, minus 3t squared, divide that by 2 as well, we get minus 9 over 4t cubed. And that's, we can simplify even further. So that's 3t squared minus 9 over 4t cubed, and that is your d square y dx squared, your second derivative. Okay, so basically the rule is this part right here. This is the golden rule. If you want to find d square y dx squared when you have a parametric equation, you have to go d dt of that derivative function. So, or in other words, y dash or dy dx. Then you multiply that by dt dx. This is the golden rule. If you remember this, then you won't fail when you see these questions. You go d dt of the derivative function, the gradient function, then multiply by dt dx to get rid of dt's, and you should be able to solve this. So good luck with that, and hopefully you are able to do the question on the textbook and have fun.